You ever write a Spark SQL query and you're just blown away by how fast it runs, even on these huge data sets? It feels like magic, right? Well, today, we are going to pull back that curtain. We're going to peel the onion layer by layer to see exactly how Spark SQL pulls off that incredible performance.
And yeah, that's really the core question we're tackling here. You type out a simple select statement, or maybe you chain together a bunch of data frame operations. You hit run, and then boom, you've got your answer. But what is happening in that gap? How does Spark take your simple request and turn it into this super efficient distributed job? That's the journey we're about to go on.
All right, so let's start with the very first layer of the onion. What is Spark SQL from your point of view as the user? At its heart, it's the part of Apache Spark built specifically for structured data. But honestly, it is so much more than just a SQL engine. You know, the thing that makes Spark SQL so flexible is that you're never locked in. You can write your classic SQL, or you can weave it right into your Python or Scala code. You can pull data from a dozen different places, Parquet, JSON, your Hive warehouse, and it all just works together through one clean API. And under all of that, this is the real secret sauce, is this promise of automatic optimization. That's what we're here to figure out.
You know, to really get why this is such a big deal, it helps to look at what came before it, the Spark Core RDD API. With RDDs, you were in the weeds. You had to manually figure out the best way to transform your data. Super powerful, sure, but also super complex. Spark SQL came along and gave us this higher-level world of data frames. And, most importantly, an automatic optimizer. It was an absolute game changer for both speed and just getting stuff done.
So let's peel back that next layer. Here we find the thing you're actually working with day to day, the data frame. If Spark SQL is the whole system, just think of the data frame as its core component. Kind of like a database table, but with a whole bunch of superpowers. And that really is the easiest way to think about it. It's a table. It's got your columns, like name and age, and it's got your rows of data. The big difference, though, is that this table is spread out across a whole cluster of computers, and it has some really special properties that make it wicked fast. So what are these special properties? Well, first, it's schema-based. It knows that the age column is full of numbers and the name column is full of text. That's critical for optimization. But the real magic here is a concept called lazy evaluation. When you tell Spark to filter a data frame or join it with another one, it doesn't actually do anything. It just jots it down in a recipe book. And that right there is the magic trick. Because of lazy evaluation, Spark just waits until you say, "Okay, I'm ready. Show me the results." Only then does it look at the entire recipe you've built. This gives the optimizer the full picture, letting it shuffle steps around, combine things, and find the absolute fastest way to get you your answer before it even touches a single piece of data. And that brings us right to the heart of it all. The brain behind the whole operation, the Catalyst Optimizer. This is where your nice, simple query gets transformed into a highly optimized, lightning-fast distributed job. I love this quote because it's just so true. For so many of us, Catalyst is this thing in the background that just works. It makes our code fast, we don't have to think about it. But today, we are prying open that black box. So Catalyst works in 4 main stages. First up is analysis. This is just a sanity check. Do these tables and columns you mentioned actually exist? Next, logical optimization. This is where it gets clever. For instance, if you have a massive table and you filter it for country equals USA, Catalyst is smart enough to push that filter down to the data source. That means it only reads the US data in the first place instead of loading the entire planet's data into memory just to throw most of it away. Huge. Then there's physical planning. Here, it comes up with a few different ways to get the job done. For a join, it asks, should I do a slow and steady sort merge join, or is one of these tables small enough that I can do a super fast broadcast join? It actually uses a cost model to pick the best path. And finally, code generation, where it turns that plan into super efficient bytecode that runs natively, cutting out a ton of overhead.
Okay, but Catalyst makes its plan before the job even starts. What happens if its assumptions about the data are wrong? Well, that's where our next layer comes in. This is a feature that acts like a genius in the middle of the query, adaptive query execution, or AQE.
This is the exact problem that AQE was built to solve. You know, maybe Catalyst thought a table was small enough to broadcast, but whoops, it's actually way bigger. Or maybe your data is really skewed, where one partition has 1,000,000 rows and all the others have 10. That can create a huge bottleneck. The initial plan can't always predict the reality of the data at runtime. So, what does AQE do? It watches the query as it's running. If it sees an operation that creates thousands of teeny tiny inefficient files, it'll step in and merge them into a more reasonable number. If it finishes one stage of a join and realizes, hey, this table is actually small enough to fit in memory, it will literally switch from a slow join strategy to a much faster one, right in the middle of the query. It can even spot those big, skewed partitions and break them up into smaller chunks to keep all the machines in the cluster equally busy. It's re-optimizing on the fly based on what's really happening with the data. Honestly, the best way to think about it is this. Catalyst is like planning your route on a map before you leave the house. But AQE is your GPS with live traffic updates. It sees the unexpected congestion and reroutes you on the fly to make sure you're always on the fastest path. Okay, so we've optimized the plan before we start, and we're adapting it while it's running. How could we possibly squeeze out more speed? Well, the final layer is to just rip out the engine and replace it with a supercharger. This is Photon. And it's like taking your family car and getting a Formula One engine dropped into it. The standard Spark engine runs on the Java virtual machine, and it processes data one row at a time. Photon is a total rewrite in C++. It's a native engine, so it talks directly to the hardware. But the biggest difference is that it uses vectorized processing. Instead of chugging along row by row, Photon grabs huge columns of data in massive batches and processes them all at once.
So how does that work at the hardware level? Well, modern CPUs have this amazing trick up their sleeve called SIMD. That stands for Single Instruction Multiple Data. It means the CPU can take one command, like add these numbers, and apply it to a whole chunk of data at the exact same time. Photon is built from the ground up to take full advantage of this, which is why it's so incredibly fast for those big, heavy analytical queries.
And the results, they can be absolutely mind-blowing. For the right kinds of jobs, we're talking about a performance boost of up to 12 times. It is a true supercharger for Spark SQL.
So I've gone on this whole journey, from the high-level data frame you write your code with, down through the clever planning of the Catalyst optimizer, into the real-time adjustments of AQE, and finally all the way to the bare metal speed of the Photon engine. Each layer just adds more and more automatic intelligence. It really leaves us with a fascinating question to think about. As these systems get smarter and smarter, what's the future role for us, the developers, when it comes to performance tuning?